We are on the page 39, section 2.5. We are going to talk about something called chain rule, another rule, right? So far we talked about many rules like constant rule, power rule, sum difference rule, right? And we also learned product rule and quotient rule. So all those are the basic tools for doing what? For doing the derivatives, right? Now we are going to learn some more advanced tool. It's called chain rule. Before we talk about chain rule, and we are going to talk about something called higher order derivatives. So we are going to talk about more derivatives. Derivatives are the skills you are using to do the problems, right? So let's see. We are going to use more skills on the derivatives. First, we learn, the symbols and notations, and then we learn the concepts, okay? Then higher order. Remember, we just learned the derivative. We use prime. That's called first derivative. Then we are going to go higher, and all the way to the nth one. So let's use some notations. So one is the prime notation. We did the derivatives, right? For derivatives, we did what? F prime of x, right? So we say it's the same thing as what? We say y is your f of x, right? So you take a derivative, that means y prime. Then we also use another notation we have learned is Leibniz notation. He is a German philosopher, mathematician, okay? He used this symbol to do things. So we write, so for the f of x, we did earlier for the first derivative, okay? Also, Leibniz, he also uses this notation, okay? Like when they use dx, dy, okay? Or delta x, delta y. So this one is the difference of the x, difference of the y. Remember we learned y1, y2 minus y1 over x2 minus x1 in your algebra class for the slope, right? So that means we use the difference of the y, we use delta y, or difference of x, we use delta x, okay? And this is a finite increment. It means what? The difference between certain point, okay? Then this one, when we use d, it means what? To represent infinite small increment. Of x and y. We just need to know what it represents, right? And infinite small. is the concepts we use in calculus to develop all those tools we are using, okay? But for our purpose, we are just going to using those tools, okay? So let's see, as long as we understand the notations, what do they mean? Okay, so first of all, we introduce kind of different notations for the moment. Okay, so we have like this one, right? D f of x over dy, it means what? You can write it this way because y is f of x. So we will write what? dy over dx, right? Then y actually is your f of x. This is your variable function. Then, in the meantime, remember we say prime, the original idea is from limit, something very close, you know, super close to x. So that's what it means, infinite small increment, okay? Once I have these concepts, then don't worry about it. Then we just find out what kind of tools we have, then use it, okay? Let's talk about, before we talk about new tool, chain rule, we are going to talk about something more about the derivatives. This is the first derivative we learned, right? And let's see, let's do the notations first. So for first derivative, we use what? F prime, right? Second derivative, we use what? F prime prime, okay, of x, or we use y prime prime. Either way, right? Then third derivative, what do you think? Then you use 3 primes, then or you use y prime prime prime, right? Then all the way to the nth, so that would be you put nth there, this way, and y and this way. We write it this way. And we just introduce all those symbols all the way to the nth. Nth means what? 1, 2, 3, 4, all the way to 100, things like that. Right? But not infinite. Then for regular calculus class, infinity is a big time, very important concepts there. Okay? But for our purpose, we use up to second derivative. Then we see how it works out for our applications, right? So let's do the notations first. Prime prime means what? Right? You take a twice. So take a twice of the d things, right? This is once, twice. How do we write? That means we do it twice. D square. Actually, we don't call it d square. Okay, we write it this way. All right. Then f of x means what? Y. Or if we use y prime, we will write it this way. D second, then y dx to the second. Okay? For the convenience, sometimes we use prime prime of the function. When we do the calculations, we use a lot of d over dx from that German guy, Leibniz, right? Then he invented this notation for us to do what? to calculate. Okay, it's just help us to do things easier with notation. Okay, so for this one, 3 times, so you write 3 of them, then the x 3 of them of f of x. Or if we do y, we do the 3 of them of y and dx to the 3. Okay, to the nth one, so that will be dn dx to the nth of them for f of x. Then for this one will be dn for the y to the x to the nth time. Okay, so we just introduce the symbols. We actually maybe practice up to third. Most of the time we need it to the second. We need to use that for our applications. Okay, but just in case you go further to the higher level in business, you might want to take some more advanced calculus. Okay, so you might use those symbols. It might come handy. So let's see some examples to practice the higher order derivatives. Okay, so we practice these derivatives first to know how to, operate on. Then we learn the skills. Then we see how we are going to apply them. Okay, so let's do some derivatives. So on your page 39, right? For the first example, that's your function. This is what? Polynomial function, right? So for calculus, we use functions all the time. Take a look. So we say find what? F prime, first derivative, second derivative, third derivative, and fourth one. Fourth one we can still do fourth. After that, we'll just use numbers. There. So, right? So to do the derivatives, we use what? The rules, the tools we have learned, right? What kind of tools we have? We had what? Constant rule, power rule. What else? Sum and difference rule, and what? Product rule and quotient rule, right? And subtract, multiply, and divide things. So we say derivative. For each one, you have sum and difference. So you just do it individually. Then for each one, it's power. Then power rule, you drop one level. And for constant rule, you drop to what? 0. So this one will be what? 3x squared y, right? And minus what? 6 times 2, 12, and drop one level is what? 1, right? This drop one level is 0. 1 power to x 0 power. Then only have number left. Okay, this one to 0. Constant rule. Then next one, drop one level and multiply your power to the coefficient, become a coefficient. Then you multiply another one. So that's what you will have, right? Then another level, you drop one more level down, becomes what? 6, right? Then next one, constant rule, that will be 0. So we are practicing what? Higher order derivatives. Look at the next one. F of x equals 1 over x. What do you think you would do? We don't want to do quotient rule. Too much trouble, right? Because you only have one variable, then you can just use power, and power rule is much easier. So we will do what? Change this becomes what? Negative 1 power reciprocal, right? Then we do what? Let's just do a few levels. Okay, so first level will be what? You multiply negative 1 to the drop 1 level, negative 2 power. Next derivative, that will be what? Multiply out, then will be positive 2 and drop 1 level. Is that right? And next level, third derivatives, you multiply out, negative 6, drop 1 level, right? And higher up, I can just do that. Then what we will have, multiply out, will be 24, x drop 1 level to the negative 5th power, right? If we try another level, that would be negative 120, drop 1 level, negative 6 power. Right? Are we good? Okay. Let's see next example on your page 40. On the top, we say find the derivative of this thing, right? So we can either use those dx thing or use the f prime thing, right? The early examples we had, because we give you f of x, so it's easier for polynomials, easier just use those. But if I didn't specify, oh, say this is f of x, so we just do it directly, we just use the dd things for the symbol. It's easier. Okay, so since you look at that, then it looks like what? A quotient, right? So what will we do? So we will just do these derivatives twice, right? That's what this 2 means. So you will write separately, say, okay, that's one, that's another one we are going to do, right? We do one first here, then we do it another time. So this is a quotient rule, right? Because you have quotient. So quotient rule, it says what? You take a square on the bottom, then the top, you take a derivative, one of them, then multiply another minus derivative of the bottom one, multiply the top one. Is that right? So we will write it this way. We just get familiar with the symbols we just learned. Okay? So this derivative means what? You take the square on the bottom, then you will do what? The derivative of the top, right? Instead of writing f prime x g of x minus g prime x times f of x. That's the numerator for this, right? So we will take a derivative of the first one, the top one, right? Which would be what? This derivative will be what? 2x, right? That will be this one. Then multiply what? The denominator. Can you see it? Right? That's your f prime x times g of x, the denominator. G of x is your denominator, f of x is your numerator, right? Then we say divided by the square, denominator square, right? That's your quotient rule, right? Then minus, take a denominator's derivative. Denominator derivative x is what? 1, right? Then times numerator, that would be x squared plus 1. Are you with me? Okay, that's just cleaned up a little bit. So we are saying this. That's x squared, right? That would be what? 2x squared minus what? X squared minus 1, right? Then we cleaned up. What do we have? X squared minus 1. Are you still with me? So what are we doing? We are practicing doing the higher order derivatives for second derivative of this thing, right? So we do it twice. Then when we do it first time around, the inside is a fraction, so we use what? Quotient property. So we did it for the first derivative of inside. Then we will do it again for the second derivative, right? Still a fraction, so let's do it again. So what do we have according to the quotient rule? So we will take what? The bottom square, right? So that will be x fourth. Then it says take the numerator's prime. So numerator is x squared minus 1. So you take prime will be what? 2x, right? Then multiply what? The denominator. Multiply the denominator, which is x squared. Are we good? Okay. Then minus the denominator, minus denominator's derivative. Denominator's derivative, which is what? 2x, right? Then times what? The numerator, that's this one, x squared minus 1. Are we good? So here will be what? 2x cubed minus 2x cubed plus 2x. Is that right? So we cleaned up. So that would be 2x over x fourth. Then simplify. So that would be 2 over x cubed. Are we good? Looks very complicated, right? Let's see. We can choose another approach. Okay, so we are going to do the same thing. Right? When you have more experience, you will find the better way. Okay? So you can tell whether or not you have better way or simpler way. Because when we look at these fractions, I can just divide it by x. In your 152A class, we were doing what? Division, right? Polynomials divided by polynomial. And then you have a single monomial, right? So you can just distribute. So x squared divided by x is what? X, right? And 1 divided by x is what? So this one will be x plus 1 over x. Then we write it in what? Power form. Because when we do the derivatives, we always deal with the powers using what? Power rule. So if you do that, so it means what? d dx, you do it twice, right? X plus x negative 1. Then this is rather simple for this because you have what? 2 items, 2 terms. So you can do what? Sum and difference rule, do it individually, right? To take a derivative. Then each individual just a variable with the power. Then we use power rule. So for the first one, that would be what? 1, right? Because 1 power, you move to outside, this becomes x to the 0 power and drop 1 level, right? So become 1. So that's 1, right? Then this one, you move the negative to front, then drop 1 level, right? Then 1 we can ignore, right? So then you still use the sum and difference rule. First one, constant rule is 0, so you don't have to write. The next one is a negative, then you move negative 2 to the front, drop 1 level, become negative 3. So total would be what? 2x negative 3, right? Is this much easier? Do we have the same answer? Check. Are they the same? Yes, because x negative 3 is the reciprocal, right? That would be 2 over x cubed. Are we good? Okay, not too bad, right? So let's practice some more for the derivatives. That's what we are doing, right? Quotient properties, and quotient rule is okay, doable, but it's just a lot of work. If you can use other way, then probably would be easier. Okay? Let's see. Next one. So your next one is f of x equals 1 over square root of x, right? Then it asks you to find the f prime prime for the 1/4. So what do you think you need to do? First, you have to find the f prime prime first, right? Then you plug in the number, see its value. Then we see how we are going to use this later, okay? So let's do prime prime, because I have f of x. So I'm going to use this notation, okay? But before I can do f prime prime, I have to do f prime first. And also, we prefer to write it in the power, right? So x, square root x is what? Half, right? Then you will write it in the power form, right? Then I have f of x is that. Then you can just use the power property. power rule, I mean. Okay, then move this to the front and drop one level. That would be -3 halves, right? Then f prime prime, do the same thing again. So -1/2. Then move over, then drop one more level, right? So let's just simplify it. That would be this one. Is that right? Okay. Then to find the f prime prime 1/4, what do we need to do? You just plug in, okay? That would be 3/4. X is your 1/4 to the -5 halves, right? You can use calculator to do this. Just make sure when you do the power negative, it's not minus sign. You need to use another, negative sign on your calculator. So we just do it by hand. So let's see, what does that mean? It means what? 1 over, right? 1/4 reciprocal to the 5 halves, right? Instead I do the 5th power first, I would do the root first because 1/4 seems much easier to do the root. So I would do that. So I would do what? 1/4, I do the root, then I do the 5th power, right? Then what do I have? That would be 3/4. So 1/4, take a square root, that would be what? Half to the 5th power, right? Then what is 1/2, take a 5th power? That would be 1/32. Right? Okay. So 1 divided by 132 means what? 1 times 32 over 1, which is 32. Right? So you can just do that 3/4 times 32 over 1. Then you 8. Then that would be 24. Got idea? Okay. Then we practiced what? How to find the derivatives. And to the second level. At the same time, we might give you a value, then ask you what's the result. Okay? To plug in the number. Then we see how we are going to use certain numbers for the second derivative. Then how we are going to use it later. Okay, first we find the value first. Good? So we are practicing what? Higher order derivatives. Let's take a look at the next example. Predicting population growth. Okay? So it says, United Nations demographers predict that T years after certain times, T years from the year 2010, okay? And the population of the world would be what? To give you population of T equals 6900 plus 198 T to the 2/3 power. What are they talking about? So P of T is Y, T is your X. From T to the P, from X to Y, from T to the P, means what? From the year to the population. That's what we are talking about, right? So this is the model given to you, okay? So What does it tell you? So what do? You do analysis, okay? Plug in some numbers, see it starts to make sense to you, okay? So let's take a look. Okay, what happened? 1. What does 1 mean? It means what? 1 year from 2010, that means what? 2011. At the year 2011, how many population that would be? Okay, so you plug in 1 calculator, then you find out it's 7098. Okay, so that's year 2011, right? That's just listed out all the years. So you just use calculator, right? So just list out everything for you to kind of connect what's going on and what does this function mean, okay? So I wrote it down. That's 7214.03. That would be year what? 2012. That would be this 11.85. This would be 7398.93. This would be 7478.96. The 6th year after 2020, that would be 7553.78, right? Not only say 7,553, it's by the what? Million. It tells you that's how they calculate it. Millions people. Okay, so that would be this one. Then this would be for the 8th year after, would be that. Then this would be 775670. That would be 7819.03. Right? So you know all these numbers. How many millions people that would be according to the model given. This is just a model. Some people did a study and find out that if you use this model, you will predict things kind of accurately. Okay? So, let's take a look at the question. It says, find the p prime of 8 and what? P prime prime of 8. Then see what it means. So first we find the numbers. Then we find the meaning. Okay? According to what we have learned, prime is what? The derivative. The instantaneous rate of change. Then P prime prime is what? Change on change. Is that right? So you talk about 8. 8th year after 2010. So that would be, must be this year, right? Must be this year. That would be 2018, around this time. Is that the world population? Oh, yes. All right. So the United Nations, they did a study. So it was saying, oh, around 2018, we might have what? That's a million. That's what? Billion. Around 7.6 billion people. All right. Then this is a 2019. So this would be what? This is 2018, 2019, 2020. Okay, let's see, we are 2020 now. So according to their model, let's see how good their model is. Okay, so if we do P prime of 8, that means we are talking about at year 2018. Okay, so if I wanted to do P prime, I have to do P of T prime first, right? That would be 0. Then I do this one, that would be 2/3 times what? 19. I should write this way better. 198 times what? 2/3, drop one level, right? So that would be 132 t of negative 1/3. Okay, then I do p prime prime because I need to plug in the number. So I do that again. 132 times negative 1/3 t of 4/3. Okay, so that would be what? You will have negative 44 t to the negative 4/3. Okay, then let's do p prime of 8. Then see what does it mean. Okay, so p prime, I'm going to plug in p prime of 8. Then you use your calculator, right? Then you find out it's 66. And p prime prime of 8, I'm going to plug in here. Then you will find out it's negative 2.75. Then let's see what does it mean. Okay, so your interpretation would be this way. Right? That's important. Okay, what are we talking about in the year 2018? Right? 8 years from 2000, right? Say the world, we are talking about world population, right? Will be what? The rate of change means after that, then things changed, right? Is because prime means what? Instantaneous rate of change. Change on the population. The population would be what? Positive, so will be growing at the rate of what? 66 million people per year. That's what it's saying. Okay, then we take a look. So from 2018 to 2019, how much increase there is? Okay, so you subtract them. 7756 minus 7692. So the increase is what? 64.70 according to the model. According to the derivative, the way we calculate, it would be what? 66 million. Okay, pretty much very close. Then let's see. What does p prime prime means? And it's a negative. P prime prime means what? Change on change. It means this way, okay? After 8 years, okay, the growth rate, we are talking about changing means what? Population changing means what? The growth rate. Then change on change. Change on the growth rate. Okay, that's what it's talking about. Change on change. Change itself is growth rate. Then the change on the growth rate. The growth rate is what? Changing, right? But not increasing is what? Decreasing. What? 2.75 million per year at a time, right? So in other words, okay, it's saying, in other words, it's saying what? The population, it's still continue growing, right? But the growing rate would be what? It's continue to grow, but at the slower rate, right? Of what? Take a look. This year, the growing rate is what? Growing so much. Then next, from 2019 to 2020, its growing rate is what? 62 million, right? It was 64 million. Then still growing, but start to slow down a little bit, okay? So it's the growing rate slow down. Slower rate of what? U minus, if we do here, what's the difference between this? So it will be, it was 66, growing rate is this, slow down, so it will be what? 66 minus, according to the number we have, that would be what? 63.25, so about 63 million growth per year, right? So you will growing at a rate at that time 63 million people per year. See, here according to the derivatives, we will have what? 63, because you grow 66 million at the 8th year. The following year, will be slow down, growing up only 63.25 million. And according to the model, then we will, on this, the difference will be 62.33 million. Very close, right? The numbers are telling you the situation according to the model. The model is not completely accurate, but give you some sort of ideas. So we said we are going to learn something called chain rule, more advanced tool, okay? Before we do that, we introduced something more called higher order derivatives, okay? At the same time, we saw some examples about populations. So first derivative means what? The change. The change of population means what? Growth, right? And the second derivative will be what? Change on change. So change on growth, okay, will be what? The accelerations or the decelerations of the growth. So that's what we were seeing, right? So for the higher order derivatives, we use that. Now we are going to do the chain rule. Before we do the chain rule, we need to go back to review our composite functions. Okay, that's on your page 4. You take a look, page 4. So we say for functions, what do we have? So for functions, we did what? Add, subtract, multiply, and divide, right? Then we also did what? Derivative now, more advanced thing besides those basic subtract, multiply, divide. So we are going to do it more in deeper level, something called the derivatives. We are going to differentiate something, right? Let's see. And for this, for s subtract, multiply, divide, that's easy. For the derivatives, we have several things we have been talking about, the tools we use to find the derivatives. We have what? Power rule, right? Many, drop one level, and product rule, right? So product rule is what? You have those functions multiply together. Then we what? Find the derivative of first one, multiply second one, plus derivative of second one, multiply the first one, right? So for the derivatives, we operate on what? The multiple of the function, right? Then we also have what? That's just to find the derivatives. Then we have f of x over g of x. If you have a quotient, then we find the derivative by certain rule, right? We have what? Take the bottom square for the derivative, right? Will be bottom square. And the numerator will be what? First numerator's derivative times what? The denominator minus denominator's derivative times the numerator, right? Then we also have what? Sum of difference. Take derivative, sum of difference. For the functions. Functions are those functions, right? For all those different functions, add, subtract, multiply, and divide, then the derivatives are operating on those functions. But we say another type of function we have is what? Compositive function. Function operates besides, add, subtract, multiply, and divide. We also do what? Compose them, stack into each other. We did that. That means what? We did this way on your page 4. So you do want to look at it, right? We have what? F g of x. That means what? You do one, then you fit into another one. So that's another operation of the function. Then we wanted to do what? Operate on those for the derivative. It's a little bit different from those. When we operate on, we want to find the derivative for this. We want to find the derivative for this, right? So when we want to find the derivative on the composite function, then we have to do a different way. It's called the chain rule, okay? So we see. So let's review the composite function first. We are on your page 41, right? On your example, we have this. So we say if f of x equals x squared, g of x is 4 minus x. We want to find what? Find f g of x. So that means you're fitting one function into another function. So what do? We say you do it the closest one first. You replace g of x by whatever you have, right? Then you will use the result to feed in to the f. Then f says, whatever you give to me, I'm going to square you. So whatever you give to me, I'm going to take a square, right? Then now we feed in what? With 4 minus x instead of x at x place, right? So you write 4 minus x squared. That's how we fit in, right? So that will be the fg of x. Then the purpose we are talking about the composite function again is we are learning the derivative on a function. So on the functions, right? So the derivative can be taking on the functions with sum and difference, multiplication and division. And also the derivative, when we take derivative on a composite function, that will be different. Okay? So if we say, if I want to take derivative of this one, 4 minus x squared, right? Take a derivative on the composite function on this one because this has been, composed, not just a simple one. Because inside you have square, you have inside, but you can multiply out by what? You can multiply out and do the derivative, right? That's doable, right? However, if I have these things, I have things like this, for d dx, if I wanted to do x squared plus 1 to the 5th power, then you have to multiply 5 times out. It takes a long time, right? Then it will be what? It's not desirable. Because this is not a single thing, x to some power. If you spell it out, it would be x to the power. Then we can do it individually by power rule, right? Simple. But if it's this one, it takes forever to multiply 5 times. So we really don't want to do that because this one is composite function. Because you have this one and composed then into a 5th power, right? So if you look this way, if for this one, how can we compose it? That means what? If for the 5th power is later, so if we want to compose 2 of them together, right? Then f means what? The 5th power. Then g of x means what? The inside. So it would be like this. So your g of x would be what? The first thing you do would be x squared plus 1, right? Then your f of x would be what? X to the 5th power. If you compose together, that would be this one. So we have composite function. But if we want to take a derivative on the composite function by multiplying 5 times, that's a little bit, too much work. So it's not desirable. So we will use another tool called chain rule to do the derivative of composite function. That's what we intend to do. Okay? So let's see, what are we talking about for the chain rule? Okay? So advanced tool, and it's saying this. That's on your page 41, right? So the chain rule is talking about this. Chain rule means what? It's a chain of actions. Like composite function is a chain of actions. So you have this action first, then you put it into another action. Right? So chain rule is saying, if I'm going to take a derivative of a composite function, what I need to do? That means I'm going to take a derivative of this guy, but inside is not that straightforward. I also need to multiply the inside, the derivative of the inside. Because you have a chain of event, so you have to take the derivative of the inside, then fit into another outside one, then you have to take a derivative again. So it's a chain of actions. Okay? So if for the nth power, so in a generalized, okay, if generalized power rule, it's saying this. That means if I have d dx, take a derivative of g of x for the nth power, just like this one. I have the g of x is x squared plus 1. I have nth power, right? Instead of second power, you can multiply out. But if you have, say, fifth power, sixth power, it takes forever. Okay? So I would take the whole thing, take a derivative, treat of g of x just as is. Then by power rule, I should have what? I move the n to outside, right? Then I drop one level of the function, right? But it's a chain event, so inside is not that straightforward. If it's x, you just do the x, right? If inside is not just a x, then because it's a chain of action, before it happens, it has to what? Take the derivative itself. Okay? That's the chain rule. And so it's more steps for the tools you need to use. Okay? So this is a little bit more advanced than to handle different situations. Are we good? So we are operating on the what? Functions. Then functions have add, subtract, multiply, divide, and composite function, right? Then when we take the derivatives, we are learning the derivatives mainly, right? Then we will operate the derivatives on those different operations of functions. That's what we try to do. Okay? Then we use the chain rule for the more complicated situation, which is composite function. Okay? That's what we are doing. So let's practice the skills first about the chain rule. Then we see some examples. So first one, use the chain rule to find the derivative of this. Something to the 10th power, right? This one is, we can use what? Generalized power rule, because you have something to the power. Then it says what? Treat the whole thing as a single one. Then to the power, with power rule, you to the move the coefficient out. Then you drop one level, right? Then, because inside is just not x, you can do that directly. Because inside is more complicated. From the chain event, chain actions, the inside need to do the derivative as well. That's what it's saying about generalized power rule. Okay, then cleaned up. So this one is what? 2x minus 5, right? Then you multiply this. You can just leave the answer here. Okay? If you don't use the chain rule, it will not be correct. Let's see some situations to explain why the chain rule is critical. Okay, so let's see some examples. This one is not on your blank paper. Okay, so if I have f of x is 2x plus 5 to the square, right? If I take a derivative of x, then I just multiply them out so I can see what happened. So when I multiply them out, would be what? Trinomials. A trinomial, right? Plus 5 times 2, 10, 20, double, and 25, right? Then I take a derivative of this, that would be 2 times 4, ax plus what? 20. That would be the result, right? If we don't use the chain rule, okay, what will happen? If we say, okay, if I just say square, then I take a derivative, I move this outside, then I will have what? 2 times what? 2x plus 5, drop one level, that's 1, right? So I multiply them, that will be 4x plus 10. Is that right? Incorrect. Right? If we take a derivative this way, then we just use the power rule, then you got a different answer. Why? Because the inside is not just x. If it's just x, you can do that. But the inside, according to the chain events, inside needs to take a derivative twice. That would be 2. Then you multiply, then you'll be fine, right? If you don't use the chain rule, then your answer will not be correct, because the correct answer should be this one. See the difference? Let's see some more examples of the chain rule. Okay? For the second example, so we have square root. If it's square root of x, you can just do it with the power rule, right? But within the square root, you have more complicated situation. It becomes what? A chain rule. You have a chain of event, right? So we need to apply those. So how should we start? That's a square root. So you always make as a power, which is half. You cannot apply half and multiply them, right? It's totally different thing. Okay? Then what should we do? Then we can use what? Generalized power rule. So you do what? You take a power because it's something to the power, so you use power rule, but with generalized because the inside is not a simple x. So you do that, right? Drop one level. At the same time, by chain rule, you need to have what? Take a derivative of the inside. That's what it's saying. Right? So this one remains the same. Then take a derivative of this one. Then this is just a regular, right? Sum and difference of the functions. Then take a derivative individual one with individual variable with its own power. So you can do it directly. 3 times 3 is 9, and oops, that's Q. Drop level is 2. For constant, that would be 0. Okay, so you can leave answers this way, or because they have, so you can do what? Then you can move this as a reciprocal. 2 is denominator, then reciprocal of the square root, right? Then this one is your regular numerator. I believe your homework, the computer will take either one of them. It should be okay. All right. Look the next example. We are practicing the chain rule, right? So you have power, then you know you can use what? Power rule. But the inside is not single x. So you have to use the what? Generalized power rule. So that would be what? So take this one, move the coefficient, move the power to the coefficient. Then you drop one level. At the same time, you need to find the derivative of the inside, right? Then, oh, not a good idea, because what? Oh, quotient rule. So I say, okay, too much work. Then what do I do? Can I do that? How about I just write x squared plus 1 to the negative 3? Would that be better? So I don't have to deal with the quotient rule. Okay? So I just use the power rule. Same thing, the power, generalize the power rule with the chain action, right? So that will be -3 and drop one level, right? Would be -4. Then I would take the chain action inside. For the inside, using what? Chain rule. That would be much easier than dealing with quotient, right? So I will have this. That would be 2x, right? Then definitely if it's simple thing, you just put it together, right? Or you can write it as what? Fraction at the end to the 4th power. You will end up the same, but that's kind of complicated. You see, you take a square of this in a denominator, then this is square in a denominator, you end up a 4th, right? So it would be easier if you can just make simple power with negative power instead of doing the fraction. Are we good? Let's see some apps with the chain rule. On the page 42, number 4, finding the growth rate of an oil slick. It says an oil tanker hits a roof, and after T days, the radius of the oil slick is written this way: R of T equals square root of 4T plus 1. So R is what? The radius, right? The radius is measured by miles. Then radius is a function of what? Time. From the time to the radius. It's like you're from your x to the y, right? And what it says, how fast is the radius of the oil slick expanding after 2 days? So time is by days, right? So it's like your oil tank, something like that, right? Then the oil slick like this. Then the radius is how it goes in 1 hour, 1 day to here, 2 days to there, right? By this function they studied. What was the question? How fast is the radius of the oil slick expanding? That means, okay, 1 day gets here, 2 days get here, right? So 1 day, 2 days, then how fast it's expanding more and more and more, quicker and quicker. So the question is what? How fast it goes. It's not saying how big the radius is, right? So how fast it goes means what? The changing between days, right? If it's finding the changing rate, the rate of change, we are going to find what? The derivative, okay? So we are going to do the derivative this. So you do d dt of what? RT, right? Which is this one. Then, as usual, if we can change it to the power, we do it with power, So we will change this to what? 4t plus 1 to the what? Half power, right? Then if inside is not just pure a variable x, it has something else, then it becomes what? Composite function. Then we have to use what? Chain rule or generalized power rule, right? So we use the generalized power rule. So what do we have? So we take a derivative, the power, that would be, put a half there and drop one level, would be negative half, but inside is not pure, just one variable x. So not only t, so you have to do the chain reaction in it, right? So that would be what? 4, and 4 times half, that would be 2, 4t plus 1 to the negative half. Is that right? So the question is, how fast the radius expanding after 2 days. So 1 day is here, 2 days here. Then wondering how fast it will go after that. So at the day 2, so t is 2, you plug in, so 2 and 4t is 2 plus 1 to the negative half. That would be 9, right? 2 to 9 negative half. Then that's a reciprocal 1 over 9 to the 1/2 power. So that would be what? 3, right? So 2 times 1/3, what I mean. So 1 is a reciprocal. So that would be 2/3. 2/3 of what? Dollars, goats? No. It's what? Miles per day. We are talking about the changing rate. It's not to say expand, right? It's not say, okay, it will be 2/3 mile at that day, okay? So if you do the analysis, so the day 1 is square root of 5, right? You plug in, and that will be around what? 2.236 mile. So that would be around here, 2.236 mile. And second day, that would be what? 3 miles, right? So what does T2, then take a prime derivative, then it says what? It will increase by 2/3 mile a day. So after those number, right? After 2 days, it's saying, okay, the radius of the oil slick is growing, right? It's growing at the rate of what? 2/3 miles per day. So first is this around 2.236 miles. So when it gets 3 miles, it means what? It increased how many miles? Between 3 and 2.236. So 3 minus 2.236, it's about increased by what? 0.64 miles, right? 0.764 miles. Then next day, it will expand what? 2/3 mile. So that will be point around 666 mile at the time. So according to this model, you can see first it's 2 point some miles, then it will expand, right? More and more and more. Actually, the expanding behavior is what? Little bit less each day. According to that, is the rate of change at the time. Okay? That's what it's saying. Then, because this model is what? More complicated, with radicals, with something inside as well. So we need to use what? The chain rule. Okay? Different tools to operate on the different situation, more complicated function. So we can look at the problem this way as well. The model says the radius is the this function according to the days. First day, you plug in, so it is saying that it will have how far the oil slick would be, right? So that would be about, say, 2.236 miles. So it will expand the oil that way, right? Then after day 2, it will be total how many miles? That would be 3 miles. So total would be what? 3 miles, right? Then the third day would be what? 3.605, right? So that would be like this. Total would be 3.605 miles. Then a day after, it would be more. It would be like 4.123 miles. That's what I say, right? According to the model. Then the question was what? How fast is the radius of the oil slick expanding, right? How fast is going to expand? So take a look. After first day, how fast it will expand? So according to the model, you will add what? Add 0.764 mile here. And next day will be what? Plus another 60.5 miles. And another day will be what? Plus another 0.518 mile. Right? According to the model, that will be what we have. Then, according to the calculation of the derivative, what is saying, right? Derivative means what? The rate of change, at the time. So after 1 day, it will be what? 0.894. So that's the day 1, right? The day 2 will be what? The change is not the total, it's the change is what? 0.66. Then first one, it will be 0.894. The third one will be what? 0.1554. That's what it's saying, how fast it's expanding. So for this question, and the answer will be what? After day 2, the change will be what? 0.666 mile. That's what it's saying. Okay, you can either see it from the model, from the difference of distance, or from the derivative. They are very close. Sometimes it's not exact. Okay, but to give you a general idea what's going on. So what do? You can just plug in the 1, 2, 3, 4. This will be your what? Analysis method you will use. And or you can use what? Find the derivative, the different tool, right? To figure out the change as well. So it is saying after 2 days, right? The radius of the oil slick is growing at a rate of what? 0.666 mile per day. Then on your page 42, number 5, we are going to deal with this later because the function, the power is on the variable is on the power position. So it's different from you use a variable at the base. Let's see some more examples. On your page 43, okay, let's practice some more skills. Number 5, then we have more complicated situation. So sometimes your model for the apps like this is complicated, so then you need to use the chain rule. So like this, so we start to practice the skills, right? So how should we start? It's polynomials, so you don't want to multiply them out, right? Takes forever. So you have 2 parts. These 2 parts are what? By multiplying, right? So if multiplying, then we can use what kind of rule? Product rule, right? Because they are multiplying. So we just kind of separate them with that first. So we will do what? dx for the first one, take a derivative times the second one, right? Plus the second one, take the derivative times the first one. That's the product rule, right? Then for this one, take a derivative, then you have a power applies to the inside. But the inside is not just x. Then it will cause chain reaction. Then we'll have to use chain rule. So for the power, you take out, right? To use the generalized power rule. So you take a 3 out, 3x plus 2. Then we have to take the derivative of inside. So that's that one. Then multiply this, right? Then for the second part, you take this 4 outside, then you drop, wait, I need to drop a level, right? So I drop the level, then I take the derivative of inside, right? Then multiply this, or multiply this one remaining one, which is this. Can you see it? Okay, Let's see if we have any typos. Okay, so this one would be what? 3. So 3 times 3 would be what? 9. So we have 9 times this one. That's got that one. And with also this one, right? And this one, we take a derivative, it's 2. 2 times 4 is 8. So I have 2x minus 1 to the cube. And remaining portion is this. Let me see if we have any typos. Okay, that looks all right. So we can just answer the problem this way. That's good enough for our purpose. Or we try to write in the factoring form, okay? So we write the factoring form, that means what? We can solve equations, right? So if we try to factor it, we can just take out 3x plus 2, 2 of them. Here is 3 of them. So we can take out 2 of them, right? Then here is 4 of that. This is 3 of the 2x minus 1. So we can take 3 of them out. Then what's left? 2 out, 1 left. So you have 9. 9 times 2x minus 1, right? Then here, 2x minus 1, 3 out. Then this is 3, you have to take 2 out. So you have what? 8 and 3x plus 2. Right? Then we just cleaned up. So that would be 3x plus 2. Take the square. 2x minus 1 to the third. Then we cleaned up this. Combine like terms. Then you will have 42x plus 7. But if you like this, we should be able to take out another 7, right? So it would be this way. Then you copy down everything else. So that would be 6x plus 1. So if you write it in factoring form, factored form, it should look like this. Either way is fine. Okay? And this one is easier to solve. If we need to solve the equation, we put it equal 0, then we solve it. But for the derivatives, we just do the what? Individually by product rule. Then after product rule, then for those, we need to use what? Chain rule. Right? Let's try some more for the chain rule. Okay, so number 6, we have this to the 4th power. Then look at this one. Actually, it's really hard to divide. If your denominator is a mono, right? Monomial, then you can just split. But it's not. You can't. So you have to keep it as a quotient, right? Then this is the whole thing, complicated one, not only a base x with power. So let's use generalized power rule. So what do? We do what? Drop one level, right? Drop one level, put the coefficient there, drop one level, then do the chain reaction. Okay, so you have to do the inside for the derivative as well. And this one is just that. Then this one is what? The quotient. Then we need to do what? Quotient rule. So that will be for the fractions, that would be the denominator square, right? Then the numerator is what? You take the derivative of the numerator times the denominator minus what? Take the derivative of the denominator, right? Times the numerator, right? So for this one, what do we have? X plus 1 squared. This one is just x. Derivative of x, that would be 1. Times this would be x plus 1. Right? Okay, so that's 1 times this. And this one, take a derivative, that is still 1 and times x. Right? So that will be 4x over x plus 1 to the cube. Multiply this. This will be x plus 1 minus x. That's 1. And this would be what? X plus 1 to the square. Right? Then we just kind of clean them up. So by doing what? Put together numerator with numerators. So 3 of them plus 2 of them, we have 5 of them. Then the top is what? X cubed with 4. So that would be the answer. Right? What are we doing? We just did more practice on the what? The chain rule with what? Generalized power rule. When we have a quotient there, then we have to use what? Quotient rule as well. Next one, we have take a derivative regarding to the z. Okay, so the inside is complicated one. Then take a 5th power. If you have a power within, in there is a function, another function, right? So you have to do the power derivative and also the derivative of the inside. Okay, so for the derivative for the power, you use power rule. You drop 1 level, right, with coefficient outside. So that would be 4, right? Then you have to take the chain rule for the inside. Right? So this is this. This one, you take a derivative for inside, you have 2 parts. And you can use what? Sum rule, sum and difference rule. So you separate them. So that will be dz. So 1 is what? Z squared, right? Plus dz. 1 is z squared minus 1 to the cube. Right? This one is just a simple variable with power, so you use power rule. That would be 2z, right? But this one, you have power, but within the power, you have another complicated situation. So you have to follow the chain reaction, keep going until the inside is the simplest one. Okay, so for this one, you use a generalized power rule again. So that would be what? 3, drop 1 level, z squared minus 1 squared, right? Then you take a dz for the inside again. Okay, so this one will be 2z plus multiply this square, right? And this one will be another 2z. Are we good? Okay, so this one will be what? 2z plus multiply them 6z and z squared minus 1 squared, right? So whole thing would be like this. If you leave that, that's good enough. Or you can multiply out, but we don't really need to do that. Okay? Because we are not doing polynomials, we just show the work of the derivatives. So we copy this down, z squared minus 1 to the q to the 4th power. Okay, so that would be the answer. I don't know how your homework, want you to do. Just try that, see, the computer will take it. So far, we talk about different tools, right? Different rules. The basic ones were what? Constant rule, power rule, sum difference rule, product rule, and quotient rule, right? And we just learned what? The chain rule and generalized power rule, okay? Or we can say generalized what? Chain rule as well. They are the same. Okay, two particular things we need to take care of it is the derivatives of log and natural log, okay, and exponential function. Log and the natural log, they are functions as well, and plus exponential function. So they are a little bit different from what we have been learning, okay? So this is more advanced tools we are going to learn as well. The other things are more kind of, you can tell, right? Start to. So for the log and natural log, mainly we do the natural log, okay? Natural log is very special. You use a lot. And so it's given this way, d dx for the natural log of x, the answer is 1 over x. The proving is kind of okay, kind of complicated. But for our purpose, we don't need to know, right? As long as you can use the tool, you don't need to know how to make the tool. Okay, we just use it. Then another one, d dx, if I have natural log f of x inside, that means it's not simple x. What do you think? Then we have to incorporate the chain rule as well. So for this one, so what do we need to do? So the whole thing will be what? 1 over x. So that's your x. So what do you need to do? Will be 1 over f of x, right? And plus the chain rule, you have to take an extra step for the f of x. So you have to take a chain rule for the whatever in the x place. So the final result will look like this, f prime of x over f of x. So that's your log. And we are going to see some examples for those. Let's look your page 45. Let's do practice some logs first and also incorporate the chain rule as well. So look the page 45. So to find the derivative of this, On your paper, we say differentiate. It means take a derivative. Okay, so what kind of things we have? Multiplying, right? So we have to do what? The product rule first. So we do d dx. Take a prime of this, same thing as do the d dx on this guy, right? X cubed ln to the x, right? Since they are multiplying, we will do what? Product rule. So you separate them, so you have d dx of what? X cubed, first derivative of that, and multiply the second guy, right? And plus what? The derivative of the second guy, right? Multiply the first guy, right? Then see what do we have. So for this, that's a simple power one, right? Base with the power. So that would be 3, drop one level, and times n x. Is that right? And this one, log, take derivative, that's dx. That would be what? Plus 1 over x times x cubed. Then we do need to simplify if we can. So that would be square ln x plus what? X squared. So that would be your answer for that. It's okay? Manageable, right? Let's do second example. So if your f of x is natural log of x squared plus 1, since the rule says if simple x, you just take 1 over x. If inside is not simple x, you have to follow the chain rule and take more derivative for the inside. So you will write d dx this way, right? Then ln to something, that will be what? 1 over whatever it's inside. Then you will do the top times, right, f prime x. So you will take a derivative of the inside, right? Then derivative inside is a sum, so you use sum difference rule. First one will be 2x. Second one is a constant, that would be 0. So that would be your answer. Right? Let's look at the third one. We are just practicing the skills, right, with different tools for all the new rules we have been learning. So next one, if f of x is what? Natural log of x fourth minus 1 to the third power. So we write it this way. Instead of write the f prime, so we are going to take derivative of this. So we write the d dx, right? ln fourth power to the third, right? Then you would take what? Whatever this one becomes, 1 over x, right? So 1 over x, so the whole thing, whatever after ln, that will be in the denominator, right? Then the top, you need to take the derivative for it, right? And for this derivative, for the top, what happened? It's a power, right? But inside you have more things, and so you have to do it over again. So you drop one level, Then you take it inside for derivative again. Then take care of the chain command type of things until it becomes the simplest one, right? So you take a derivative of this. X fourth power is the simplest one, right? Because the base is only x, not like base for the power, it's more complicated. So you have to keep going down the chain to do this, to do it until it becomes the simplest one. So that would be x fourth minus 1. That would be what? 4x, right? That would be x fourth minus 1 to the cube. Is that right? Okay, then just happen this one, those are the same. You carry out a square. So the top will be what? 12x. The bottom will be x fourth minus 1 to the square. So that will be the result. Are we okay? So we just practiced some derivatives for the natural log, also with its chain rule as well, right? Then we are going to do some derivatives for the exponential functions. Let's come back to the page 44 for the exponential function. So what is exponential functions? So that means x is on the power position, exponent position, right? Or with base e. So same thing as log, we'll have base 10 or base e. For our purpose, we just use the base e for the application. So we learn those e things first. So we say d dx for the e to the x power. Okay, when we take the derivative of e to the x power, the result is still e to the x power. The reason? Probably we don't want to know, right? So we just use the tools. Say tools is designed this way, we will use it. However, if for the basic x, if it changed to the composite function, so it has more complicated situation, then by chain reactions, so you have to follow through, all right, until to the point it's the simplest one. So we will follow through as this one, same thing, but since it's not the simplest one, we need to take derivative of that thing. That will be prime of x. Okay, and one more is d dx if e to the k to the x. Just like this, f of x is not x anymore. So you follow through, but you take a derivative f of x for kx, right? Your kx is f of x. Then you take derivative of this. So you take a derivative of kx, which will be what? The k, right? So the answer will be k e to the kx. So that's another derivative we are learning. Okay? So all those we are learning what? The more derivatives for exponential function. So we did the log. Now we are doing what? The e things. So let's practice some more. Come back to your page 45, number 4. So we have this d dx, right? E to the x power divided by x. So first, you look at it, oops, it's a quotient. So we have to apply the quotient rule first, then we do it individually. See if we have to do the chain rule, right? So quotient rule, denominator take a square. Then the top is what? Derivative of the numerator times the denominator minus derivative of the what? The denominator, then multiplies the numerator, right? Then we follow it through if we need to use chain rule. So for this one, for the exponential function, the simplest form, that's it. E to the x power times x minus derivative of x is what? 1 times ex, right? So what do we have? That would be the simplest form, x e to the x minus ex, x squared. That would be your answer, right? Next one, your f of x equals what? X squared e to the x power. So you look at this, that would be what? Multiplying. So multiplying, we need to use which rule? Product rule. So you separate them, right? So you would do the first derivative times second item, right? Plus the derivative of second item times what? First item, right? Then that's the simplest form, power. So power rule, 2x times what? E to the x plus derivative of e to the x power, simplest one, just ex times x squared. Right? So that's the derivative. And look at the question. It's asking you what? Find the prime of 1. That means what? You take a derivative of f prime, so this one will be what? F prime of x, right? Then you plug in 1 for your prime function. That means x is 1. X is 1, right? So it will be 2 times 1 times e to the 1 power plus e to the 1 power times 1 squared. So that would be what? 2e. Then this one would be what? 1e. So the answer should be 3e. Right? Okay. Let's try next one. Example 6. So we have d dx of what? E to the x 4th power plus 1. So for the x position, you have x 4th plus 1. So we just keep following the chain until it becomes simplest, okay? Like a power rule. Just one base x with a power, okay? So for e to the power, we shall follow this, but with chain rule, right? Because it's not simple x here. Then we have to follow this. So its direct derivative of e, it's itself, this guy, and follow the chain rule. We need to take a derivative of its exponents, right? Then the derivative of the exponent is simple one, just sum and difference rule, right? So that would be what? Drop one level, 3x to the cube times e to this complicated one, right? Then we write the answer. Usually we put the basic thing, polynomials, in front of the exponent things. So that would be your answer. Manageable, right? Let's see some examples for exponential function. Okay, so on your page 46, number 7. So d dx to the what? E to the x squared over 2. So exponential function. So whatever exponential function, so it should be itself. And if the exponent is more complicated, so you will take the derivative again, right? Then this is the simplest one. The constant with the x as a base with power. So that would be what? You drop one level, 2 to the x, and divided by 2, right? So your answer should be what? This one would be x. So your answer should be x times x squared over 2, right? Can you see it? Okay. For the number 8, for natural log, take 1 plus e to the x power, right? So we use a natural log rule. It says what? If it's a natural log, it's 1 over the x. But if you have more complicated situation, you take the chain rule. So that would be what? 1 over x, right? For this one. But inside, you have to take the chain rule again. So that would be d dx for the 1e to the x power. Is that right? Then that would be the what? Sum and difference rule. So then that's 0. Then d dx for the e to the x power, it's itself, right? So that will be e to the x, the e to the x. Then that will be the simplest form you have. Then let's see next one, number 9. So it's kind of complicated, just for the purpose of practicing. Okay, so just in case in applications, we might need to take a derivative for the complicated model. So this one including what? Exponential and log together, but they are multiplying together. So if they are multiplying together, what should we do? Do the product rule first, right? So product rule say, you take derivative for the first guy, multiply the second guy, right? Then plus the derivative of the second guy, multiply the first guy, right? Then you will take the derivative individually. Then for this one, exponents, e to the 3x, e it's itself. However, x place is more complicated. You need to take a derivative of 3x, right? Then this one, copy down, then plus you take a derivative of a natural log is this, but the more complicated situation, it's 1 over that guy, so it's 1 over the whatever inside the natural log. Then the top, you need to take a derivative of the chain rule for the top inside, right? Then multiply this one, right? So for this one, this is a 3, right? So you have 3 times e to the 3x times what? Natural log 5x plus 7. Is that right? Then plus this one, take a derivative, is 5 times this is 5 e to the 3x over what? 5x plus 7. That will be your answer. Kind of okay? You do need to practice a lot. Okay, let's see. Next example. Some apps. Okay, here says finding a rate of improvement of a skill. So this athlete is jumping, whatever, right? Say after T weeks, how many weeks, go by, he practiced a pole vaulter can vault with this model. Okay, so if you did a study, somebody modeled an athlete's capabilities, then say what? T is what? Weeks. How many weeks he practiced. Then how high he can jump. Okay, height is the function of the time he practiced, right? That's what it means. Then it says find, this is by feet. Then find the rate of change of the athlete's jumps after 0 week, at the beginning of time, and after 12 weeks. So if you work in the sports field, then you encounter somebody did those study for particular famous athlete, then you wonder what's going on, right? So what do? You do the analysis first. So you just plug in number, say, oh, the weeks, when say week 0, what happened? How high he can jump? So you plug in 0. That would be 150 minus 11 is what? 4, right? 4 feet. Then you plug in, say, after a week, you plug in the model, you find out is he can jump 5 point some feet now. It means what? His ability increased by 1.0468 feet, right? According to the model. So you say, okay, what happened to the second week? Second week, after 2 weeks, he can jump this. Then what's the difference? He increased his ability to more, right? Higher. He can jump so high, and his ability has increased a little bit. Then we continue, say, okay, we say the question was for 12 weeks. So I'm going to start from 11 and 12. Just go around the question we have around that time. Then we find out this is just plug in, use your calculator to find it. okay, to plug in. Make sure you practice your calculator to get the same number as we have here. So make sure you are doing right. Then you find out, okay, according to this model, that's how high he will jump. Then at this time, between 11th week and the 12th week, he increased his ability by 349 feet. Then between 12th week and 13th week, he increased by what? 0.315 feet, 5 foot, okay? So this one, between 13th and the 14th week, he increased by what? Say 0.285 foot. So you can see, it looks like as time goes, then he will, at the beginning, at the 4 feet, then after that he increase, but not increase so much at the beginning. He start to increase a little bit at time, right? Then let's take a look at the question. It says 0 week at the beginning training and find the rate of change. So beginning of change. So it means what? At the beginning, how fast he can improve his jumps, right? So what do we do? So for the first question, T0, it's asking you find the rate of change. It means how fast he can improve himself, right? So the rate of change, you do the what? Derivative. So you do h prime t derivative, okay? Since the model is what? Exponential function, so you use exponential functions skill, right? This rule. So it would be what? You multiply, that's 0, you multiply out, so 0.01, right? This is this one, actually. Your k, you move your k to the front, right? So it's 0.01 negative times 11 is what? 1.1 e to the negative 0.1 t. We don't drop one level, right? For the exponential, for the x, you don't drop one level, you just remain the same. If you have k there, you move the outside. So we move negative, so you do what? You have negative 0.1, you move outside, right? Times this 1, right? You keep your e to the kx. So you keep this one, right? So I should write this one. We let negative 11, the constant stays outside, then we'll move this 0.1 over here. Use the rule, right? So we end up, you multiply them, become 1.1 e to the 0.01 t negative, right? So at time 0, we plug in. So h prime 0 would be 1.1 e to the 0, right? Negative 0.1 times 0, that's 0. So e to the 0 power is 1. It's 1.1. So what is saying? At the beginning of time, he improves himself by what? 1.1 feet. So it's about, right? What do we have from week 1 to week 2? Then his potential with this model will be what? 1.1 feet. How about second one? It says week 12. That means after 12th week here. how fast he can improve himself. So you plug in 12, right? For this one, that will be 1.1 e to the negative 0.1 times 12. Plug into your calculator, okay? That would be 0.33 foot. So that's after the 12th week. There is 12th week. Then after that, how fast he can improve himself? It's about 0.33. Here, according to the model, it's 0.315. Right? So, how we are going to conclude, what did we say? So, interpretation or conclusion, we can say is what? At the time, beginning of the time, okay, his jump can be increased by what? The jump increases by about 1.1 feet, right? Then after 12 weeks training, right? The gain will be what? About 0.33 foot. That's what this model is saying. Are we okay? Sort of, right? So we have been talking about what? The derivatives for a while. What kind of tools we can use, right? For all the rules, quotient rule, product rule, power rule, right? Even the chain rule. What happened if you cannot do it, right? So we are on the page 47, and to talk about what happened, there is no derivative. This portion is not critical for our class, but just get an idea, since we have been doing all this, we can use the tools to solve problems, to use for derivatives and to solve problems. Then, what kind of conditions we cannot use those tools? We cannot use the derivatives to solve problems, right? So we kind of have idea the situations like that. So let's take a look on the page 47. So we say what kind of conditions we can do it, what kind of conditions we cannot do it, right? For the condition, we can do it, can find the derivative, we call them what? Differentiable. Then another at x, right, at that point of time. Then another condition we call it what? Non-differentiable. Those functions are non-differentiable. That means what? You cannot use the skills we have been talking about, right? It is saying is, for first one, we have been doing that. We use the derivatives, right? We call them those points. The function is what? Differentiable at this point of time, okay? If the derivative is, we use this word defined. In math, we always say defined, means we can apply, we can use it, right? It's meaningful at x. Okay. And differentiable means what? Are those functions, right? Cannot be what? Using the derivatives, right? That's what we are talking about. Cannot be differentiated at some time, right? Some point of time means x. Okay, so let's see some examples. What do we mean by that? What kind of conditions we can do the derivatives? That's what we have been doing anyway, right? Or this week. And we see some kind of conditions cannot be done. Okay? Look at the example. If my f of x equals x squared, I mean absolute value of x, right? It says, oh, cannot be done at what? At point of time is 0. Okay? So, for, math major, we might have to prove it, but for us, we just demonstrate the idea for you. Okay? So, what happened is, let's look at the graph. So, for absolute value, and it looks, you do your t-table, at 0 is 0, 1 is 1, negative 1 is 1. So it looks like this, right? The V shape. Okay? So we say, at this point of time, if we can find the derivative would be what? The rate of change, instantaneous rate of change, or what? The slope, right? Same meaning. So for this one, you look at the right-hand side of the line. So this line, the slope would be what? Rise over run is 1, right? For this line, the slope is what? Negative 1, right? And so, at this point, at x is 0, so the two sides of slopes are different, right? So the change on this side will be what? Tendency is what? Increase by 1. Then this side is what? From here going down, so to get this point, the tendency is reducing, decrease by 1, right? So at this point, you can say the conflicting slopes make it impossible, right, to define a single number, right? A single slope. So we say the slope, right? And same thing as the derivative. Is, we say, undefined at this point. That's what we are saying, right? If we can find the derivative, it means the instantaneous rate of change and or the slope. And this side will be what? Going up. This side, actually slope is what? Negative. So that's what I mean. Then we cannot find the derivative because we say the both sides have to approach to same number, right? So for both sides, the slopes are the same. You cannot have what? You cannot have bended, right? Situation like that. So it's no, you cannot have no corners, right? At the same time, it has situation is, you know, certain points, they are jumped, okay? So let's take a look. Some examples, you can see why those functions are non-differentiable, right? So let's look at the first graph. Okay, so first one, it looks like this. So that's 1, your value, right? Then from here, it goes here and going down. So that's 1, 2, and 3, right? So that's -1, -2, -3, -4 points here. So we are talking about whether or not at those points at the time, if we can find the derivative, right? So first we have to decide, is this graph a function? If it's not, we don't even talk about it, right? Then we talk about, do they have a limit? Then if they are continuous or not, and find the value of x at which the derivative exists or not. Okay, so is this a function? Yes, right? Here say where is not continuous. So take a look where it's not continuous. So you continue, follow the path, right? But here you jump. You cannot continue the graph path. So this at this point it's not continuous. Then here says find the x value which does not have limit. So what do we mean by limit? Limit means what? The y value. So limit means what? The y values are not bounded by, right? So for this one, y value is fixed, bounded by, right? Only here, y values are different. One is here, then the both sides from left and right, they are approached to a same point. So y value is bounded by. Left-hand side is close to here, right-hand side is close here. So at this point of time, the y values are not bounded by. Okay? So when you have a jump, you don't have a limit. Then, if so, and you cannot have derivative. Derivative, remember, derivative is what? It looks like limit h to right. That's what we are talking about at the beginning for this chapter 2. So your y value, and when x is very close to each other, y value is bounded by. That's the limit, right? So if you don't have a limit, you cannot find what? The derivative. That's how the derivative was defined. So at this point, at x is 1, you cannot find the derivative. At the same time, look at this example. If left-hand side and right-hand side, they have different slopes, then you cannot find the derivatives, right? So at this point and this point, you cannot find the derivatives. So at the -3 and 3, you cannot find the derivatives. So for this portion, it might be a little bit confused for you. It just gives you an idea. If you have these tools, whether or not you can use it, use derivatives to solve problems. Like these conditions, you cannot solve problems at this point of time, 1, -3, or 3. So it is what? For things to be differentiable, it means what? The line has to be what? Continuous and no corners, right? For it to be continuous, it means what? No holes or no jumps, right? So you have a jump or you have a hole there, then you cannot do it, okay? And no corners either, okay? So, or you don't have no what? Vertical tangent line. Okay, let's see what does it mean for this one. Look at the second example. So if we have this one, we have graphs like this, -2 and -3, -4, 1, 2, 3, 4. So for -2, if the graph look like here, it goes up, bend over, and turn, right? And here, it jumped, then it goes like this. Is this a function? Vertical line test. Yes. Right? So, which one doesn't have y limit? So this point, when you have a jump, you don't have a limit. So x is what? -2, right? And which one you don't have, it's not continuous, then it's broken on the path, right? So at this point, it's not continuous. At what point we cannot find the derivatives? All those holes, jumps, and corners. So you will be at what? X equals -2 and 2. This point, when for the x values, right? And look, next one. So if we have this one, this is -4, -2, and the graph look like this, going up and close to the y-axis. And this one is 2 and 4, it's around here. It bend like that. Okay, so it's a function. Yes, vertical line test, right? At what point we don't have a limit? The y is not bounded by. So each point y is exactly there, except where? Here, right? So at x is 0, it has no limit. Then at the same time, at this point, it's not continuous. Then at what point, and we cannot find the derivative. X is 0, we cannot find the derivative, right? And at this point, we cannot find the derivative as well, because you have different slopes from right and from the left. So it's about 3.5 at that point. Yeah. Got a little bit idea? Okay. So this one is called what? Like those at the point 0, and we have what? Actually, this line is your asymptote, right? Vertical asymptote. That's what we are talking about. And no vertical tangent line, okay? Then look the last one. If we have graph this way, and here is -1, -2, so it goes like here, and come down here, and bend here, right? So that's your 3, 2, 1. Okay, so is that a function? Yes, yes, yes. And at what point of time we don't have a limit? Every y values are bounded by. Not like those, right? Jump, not bounded by. Like this one, positive infinity and negative infinity, right? No limits. And but those, this one, everything, we have limits, right? For the y values, they are bounded by. Then, is this continuous? Yes. So this one is okay. So when it's continuous, even we have a limit for the y values, you may not have derivatives because what? They bend, okay, at this point, at x is 0, and at this point, x is 3. Okay, so those concepts are not critical to us. We will give you a problem, always find the derivatives, then to use it, right? But for the math people, it's critical for them because they wanted to know when they create a tool, then whether or not they can use this tool to solve problem. Okay, sometimes it's useful, sometimes it cannot be used, right? But we need to describe it for you, and it happens. Okay, so this is on section 2.5, and we finish till the page 47.